One, two, one, two, one, two, one, two, one, two. Woo! Now, I will first go into an understanding of this problem, just as we've identified it, but basically also an understanding of the brute force. Now, the brute force tries to do something interesting, right? It tries to, hold in path what this it tries to hold in path where these nodes lead. Let's say, for instance, we are given 8, right? We know 6 points to 9 that then points to 8, right? So it tries to hold in an array this part, say 6 and 9, then 8, right? And then also have another node hold 2, 6 and 2 in a list, and then try to compare where do these guys, meet, or where do these two lists created compare, and basically hold that point as its common base, right? Or base common. I'll hold it as its common ancestor, and basically that's what we try to look at here. Now let's now get into the code of the brute force and see how we try to do this. So we call find path, and find path here is going to be a helper function in this brute force implementation, where we hold the path that is transverse to get to a specific node. Now we pass in the root of the node, and then we pass in the node, right? So to find, say, 8, we need we need the root of the node, which is 6, and then we pass in 8 to enable us find that node. Now, so when we pass in that, we also create another function, a small function within the function called checker. Now we now call conditionals. We say if we hit none, if current is none, that we should return false. So in any case where we hit a none, right, we should return false, that we haven't found the node that we came looking for, right? And then we say check is it the node we are looking for. So we say if current is node, right? So basically we are checking if the current or the value where we are comparing right now is actually the node we are looking for, and if that's the case, we return true. But if that's not the case, then we have direction, dir, as a variable name, but we're trying to represent direction, and we say we append left depending on where we turned to check. Now if checker returns true on the left, return true, else we pop the left. And if direction that append right, if checker returns right, return true, else pop right, then return false. So basically what we are doing here is that we are going to the left, and when we transverse through the left, we check if the left actually holds the node we are looking for, and if it does, we return true, we push through up the stack, because this is a recursive stack, because checker here is called within itself, so we are calling it in levels, right? And then if we go to the left and we find this, then we can go ahead to say yes, this guy is true. Then we also take that up the this thing, the stack. But remember that we've already appended left. So if in the case where that left is wrong in the direction, then we also have to pop it out of the direction so that we don't misinterpret or interpret the direction, or interpret the direction wrongly. Yeah. So we do that for the left and also the right, and at the end of the day, we return false, right? And that's if none of these conditions are met, because obviously if we pop through everything and we don't have return true when we go to the left or go to the right, that means we found the what is it called, we found the value nowhere, right? And because if we don't find the value anywhere, that's to the left and to the right, which are obviously the pointers of a binary tree or a binary node, uh, then we return false up the stack as well. So having done that, we call checker to the root, and then we see what it returns. We then return the direction of our, what is it called, our or the list of our directions. Muchas gracias. Auf Wiedersehen. Tschüss. Bye.